Yeah.
You mark this out and then wrote okay, but then you don't do this.
That's my fault. I'll take it back.
Okay.
There goes my weekend, Dr. Shirley.
Yeah?
So do we have pasta?
All right, so here's our plan for the next 2 weeks. So today and Friday, we're going to finish off our enzymes and inhibitors. And Friday, we're going to spend it just kind of going over everything about enzymes, inhibitors, kinetics. 'Cause Chapter 7 is pretty hefty in terms of the amount of material in Chapter 7. So then October 21st and 23rd, we'll just do Chapter 8. That's just basic things to know about lipids. Very short, easy chapter to kind of like end that section. October 25th, which is next Friday, we'll just do a review. So I won't specifically have questions. It's you bring the questions you want to answer, and we'll go over them. I may have a few practice questions depending on how together I am by then. October 28th is our exam. It'll cover chapters, the chapters are on this one. Chapters 6, 7, and 8. And then I'm going to be out of town, so we'll just cancel class on October 30th. Yay! I mean, oh, no good, no good. So as a warning, as you're looking ahead to your next 2 weeks, I'm not sure of how much I'll be able to answer email questions, and these chapters don't really relate real well to email questions. Like if you want me to explain enzyme kinetics in an email, it's not going to be real clear. And so that's why we have all these review days, so that hopefully I'll answer all your big questions before I have to leave. And that way, if you do have a question that weekend before the exam, it'll just be a real short, concise email I can send you back about it.
Quest is for questions, not quiz test.
Yes, sorry, questions. Q-U-E-S-T. That's because I couldn't figure out how to spell question. Q-U-E-S-T-I-T-I-O-N-S. That's what, if I abbreviate, it's because, so the quiz is coming up. Let's see. This will be a group quiz. Then we'll do an individual quiz on that Monday, just so that you can kind of pull together, right, because you're going to take the test on your own. Yeah, this time it's going to be individual test. And then we'll do no quiz that day. And then you get class off.
Well, it's not a fair.
Yeah, this individual quiz will just be kind of pulling together Chapter 7, which we should have just reviewed, so you should be fully together on it for that individual quiz.
And the quiz will be at the end of the class.
It'll be whenever class ends. Like, if there's a lot of questions and we go the whole time, I'll save the last 10 minutes. If everybody is so together and they got 0 questions, which I find really unlikely, then we'll just do it at the beginning and everybody can go home. But that seems unlikely, so. Questions on our upcoming kind of schedule? I'll leave it up there for a minute. Okay, last thing before we move away from our next upcoming things. So chapter 8 is the chapter on lipids and bilayers. There's not going to be any required homework for that chapter. But here are, I guess, 7 or 8 suggested problems for you to work through for that chapter. Just the way the timeline kind of fell out, you probably wouldn't have, it's easier just to do suggested problems for chapter 8. And so I made them mostly all odd, so you should be able to check yourself in the back of the book for those suggested problems. All right, any last thoughts or questions on that before we move on to our inhibitors?
You know who we're having as props?
What was that?
You know who we're having as props?
Not yet. I've narrowed down to a few people. It may be Dr. Breton. It may be Dr. Qualley.
He's Dr. Britton.
Yeah, Dr.
Well, he won't be able to answer any questions. So that's like the trade-off. If it's Dr. Breton, he won't be able to answer any of the exam questions. If it's Dr. Qualley, he can at least lead you in the right direction on a biochem question. Yeah, during this time. So it's.
Because we've been going over all of this in the lab section.
I think I'll be able to get Qualley to come do it. So I'm thinking that'd be your better option. Someone who actually knows what we're covering in here to be able to answer some questions. All right. Can't get it all on the screen at once. All right. So where we left off on last Friday is we had covered competitive inhibitors. So competitive inhibitors could be transition state analogs, is a molecule that looks like the transition state. Then we looked at the Michaelis-Menten equation for competitive inhibitor that includes the inhibitor. So we have a new statement with the association constant for the EI transition state, where that inactivates the reaction. Then we looked at the plot using alpha as our measurement of how much inhibitor is in there. And as alpha increases, our Km increases. Then we looked at how a Lineweaver-Burke plot changes based on a competitive inhibitor. So it's the exact same plot as this one over here. But now we've done the reciprocal on each axis. So now we have 1 over V0 versus 1 over S. And now with increasing inhibitor, the Km increases, which tells you that the enzyme's not acting as efficiently as it was because now it has a inhibitor competing with the active site. And then that was the Lineweaver-Burke plot for all that. So that is the first type of 3 that we're going to look at in terms of inhibitors. Our next type of inhibitor is going to be uncompetitive inhibitors. And that was one where there's a typo on that slide. It shouldn't be transition state. It should be uncompetitive inhibitors. So the mechanism for an uncompetitive inhibitor is that one, where it's called uncompetitive because it's not competing for active site. In this case, the inhibitor binds to the enzyme substrate complex, not to the free enzyme. Which means that now we have a new Ki expression, because before the Ki expression for competitive, let me flip back to that page. The Ki expression included inhibitor, enzyme, and the enzyme inhibitor complex. Well, this doesn't exist in a uncompetitive. So our new expression for the inhibitor constant, or the association constant of the ESI complex, is now this, because now we're looking at this, the ES plus I combined to make the ESI complex. So the uncompetitive inhibitor distorts the active site. Rendering the enzyme catalytically catalytically inactive. So once the inhibitor binds to the enzyme substrate complex, it makes this new ESI complex that can no longer react. So describing the reaction of this sort of thing in terms of a Michaelis-Menten constant, but I'm going to write in terms of the Lineweaver-Burke so we can draw it. So that's not spelled right. It should be mathematically, whatever that's spelled like. Not having a good spelling day. I apologize in advance. Oh, I'm sorry. Start that again. Sorry. I realized I'm writing the same one I had before. I was like, that's not right. That's because that was a competitive. I want uncompetitive. Well, I'll just scoot that off so you can't even see it. All right, so this is the Lineweaver-Burke for an uncompetitive mechanism. So when I write it out in this way, what would I plot on the y-axis? Same thing we've done every other time we've done this. So far, so good. All right, what would I plot on the x-axis? Water substrate. Whew, okay. If that's y and that's x, which one of these two things that's left is the slope? This guy or that guy?
First one.
First one, good. Okay, so now we have our linear equation. So now we can sketch a graph and see how increasing inhibitor affects that. Does everybody have that so I can flip it over and do a little sketch? Okay. All right. Oh yeah, this will be a good one to color code. So if you have some pencils, that's good. All right, so if I have no inhibitor, what value is alpha? Good thing to go back and look at. It's 1. So I'll label this at the top, uncompetitive. So the uncompetitive Lineweaver-Burke plot. It's an LB plot. My B is kind of funny looking. So that's my uncompetitive Lineweaver-Burke plot, starting off with alpha equal 1, which is no inhibitor. That's about right there. The intercept of the x-axis is equal to negative alpha over Km. Slope for all of these is going to be Km over Vmax. And then the y-intercept is our alpha over Vmax. We're remembering that alpha is also described as 1 plus concentration of I over our dissociation constant of the inhibitor. All right, so that's when alpha equals 1. We will now add some inhibitor. One plus concentration of I over Ki. So we go plus. So all these points are still true. This is also equal to that. Also equal to that. And then if we have our third, good so far? Good, good, good. All right, so then let's make some statements based on our graphs we just made. So when we looked at the competitive inhibitor had a constant Vmax, but the Km apparent, this over here, increased. Those are going to be the two things you're going to look at for each type of graph, how Vmax changes and how Km changes. So let's look at the same two things for our uncompetitive. So Km, the negative alpha over Km value has become more negative, which means the value of Km has actually increased because it's 1 over and negative. So as I go more negative, the 1 over value becomes more positive, which means the Km unto itself is getting bigger. Okay. That value gets more negative, which means smaller and more negative, which means my Km value, let's see, alpha is a constant, so that's bigger, which means for this to get smaller, the Km has to also increase. So, right, because I have this value is getting more negative. If the alpha value is increasing going this way, the Km value also has to increase to make the overall number smaller to go that way. Okay. And then we'll look at the Vmax. So Vmax went from 1 to 1.5 to 2. So the alpha value is increasing, which means this overall value is increasing, which means the denominator is decreasing, because they're all positive values. So overall, this number got larger. The alpha value also got larger going in this direction, which means the Vmax must be decreasing to keep the fraction about the same. What about my slope? What has happened to my slope? Increase, decrease, constant. Constant, yes. So the slopes are constant for all these. Now let me talk through this Km again, because I feel like that should be decreasing. All right, alpha is constant. -1, -1.5, -2. Yeah, that should decrease. That should decrease, because the same argument we just made with this one, where, right, imagine these are all positive values. This is 2, 4, 6. If alpha has gone from 1 to 1.5 to 2, the denominator has to also decrease, because the numerator is ruling which way I'm going. Make sense? So it's a negative value. So this is -1, -1.5, -2 divided by, if the denominator is also getting bigger, then it would go this way. But it's getting smaller, so it's going this way. No, nothing.
I feel like the denominator would be getting bigger. Because as it goes like 8, 16, 24, or whatever, it's getting smaller.
All right, let's plug in some numbers to see if I can figure this out. So if I do negative, no, this is right.
As KM decreases, the number as a whole bigger.
Bigger,
And it's
right.
going bigger negative.
Yes.
So,
It has to move to the left because the negative sign is throwing you off. It's getting a bigger negative sign, which means it has to shift to the left. So if you plug in some numbers, that should work. -1 divided by 20. Yeah. Right, so if I imagine that Km equals 20, the green point, be -1 divided by 20. And then -1.5 divided by 20. Except my calculator's not working. Apparently the 0 doesn't work. There we go. Then the blue point would be -2 divided by 20. It's getting negative smaller this way. Right, yeah. So, oh yeah, negative bigger. Bigger that way. Negative bigger. As we draw our number line, it's getting a bigger negative number. Yeah, yeah. We'll draw a number line here in a little bit if we get stuck.
you use 20 for both of them.
Oh, yeah, I can make it bigger. Enter. Oh, no. -1.5. Apparently I need a calculator that the bottom buttons work. So if I make this now 25, -2 divided by 25.
So then KM is increasing. So you're right the first time,
No, I'm right this time. All right. We'll do this. I'll just pass out my worksheet. It has everything on it. Km is the value of going all the way to the bottom.
When it's moved to one,
That is the most recent.
so it's like as a whole. And if it's going above one, then it's not very or if it's below one.
So the numbers
Numbers is bigger.
But it is
But it's not
smaller.
like negative like decreasing.
That's what you do.
Yeah, the negative sign is off. Numbers will be small. Are you can numbers? No, are you That's what I'm saying. Yes.
So it was right the first time. It's right now.
It is right now. And it's right on your worksheet. The little summary at the bottom. Km has to decrease, Vmax has to decrease, and the slope remains a constant. We'll go on to the next one, then we'll come back. And this is why we're going to review on Friday. It's a lot of stuff. All right, if you're on your worksheet, you can either look at the picture on your worksheet, or it's the next PowerPoint, C. They're pretty much the same picture. Let's move on to mix, and then we'll come back, wrap up. I moved that. That's all. I just moved the figure. to another slide. So if you're looking at your PowerPoints, that figure, it's just been shifted to another one because I wanted to blow it up. It looked really small. And the picture is right here on your worksheet, so you can do either one, mixed inhibitor. The graph, yeah, the graph is on the worksheet. That way you don't have to sketch it out yourself. All right, so mixed inhibition is the third one we're going to look at, the final one. The substrate does not reverse the effects of being a mixed inhibitor. So this is on your worksheet. I'm just going to draw it on here too. In a mixed inhibitor, the inhibitor can either bind to the unreacted enzyme, or it can bind to the enzyme substrate complex. It is able to do both. Yes?
It says in the book, a competitive inhibitor, how is it affected so the apparent Vmax is lowered and the apparent Km is lowered at the same degree?
Yes.
So they're both lowered.
They're both lowered, both decreased. Yes. That is what the worksheet says. I was thinking when I got the worksheet together.
Are we gonna have to like
Understand that? I think looking at the graph, you should be, so either on a test, I'll either have you tell me the points on the graph, right? Like, so point out where Vmax is, where the Kms are, and then draw me the direction of the inhibitor. So I'll probably get rid of these alphas and be like, which way is the inhibitor going? You know, which one is the direction, like inhibitor in this case is going this way. Or, not any of the three one we're looking at. The three we look at, all the graphs look the same in terms of which direction the inhibitor goes. But the critical points of where the Vmax and the Km land are slightly different, which is how, which we'll get to, which is how you can tell which inhibitor you have. It's based on how the Vmax and the Km change.
what's the other way with the other test? You said that was one way with them.
Oh, so either I'll give you a graph and you kind of fill in the points, or you give me a general sketch of the graph where I say, draw me what the line revert plot of a mixed inhibition would be. And you just have to show that it goes, that the Kms are tight together and the Vmaxes have changed, but the slope overall has changed also, right? Because the slope's going this to this to this. Or in the previous one, it was 1, 2, 3. It's on the worksheet. It's because I was going to draw it, but apparently that was going poorly. So we'll just all look at the same picture. All right, so mixed inhibitor. The inhibitor can bind to either the unreacted enzyme or the enzyme substrate complex. We're looking at the graph. That one is alpha equals 1, which is no inhibitor. Actually, alpha equals alpha prime, right? Because now I have two different ways this combines, which means now I have two different Ki values, each with their own alpha. So since the inhibitor can bind in two different ways, we have to have two different Ki values. And then each Ki value has its own alpha that's affiliated with it, which is inside your figure. You can have alpha, which is related to Ki, or you can have alpha prime, which is related to Ki prime. because the alpha is a measure of how well that inhibitor is binding, so you have to have two different alphas because it can bind either here or here. All right, so this is our regular alpha equals alpha prime, which equals 1, which means there's no inhibitor at all. This slope means we have some amount of both alpha and alpha prime are both greater than 1. The color I'm going to use is red. Then we have this one, which alpha is equal to 2, alpha prime equals. So again, increasing inhibitor in that direction. Then on your worksheet it's spelled out. I'll just go ahead and do it up here too. For a mixed inhibition, Vmax decreases. But the Michaelis-Menten constant can increase or decrease, depending on the ratio of alpha to alpha prime. Because Km is down here, it's our x-intercept, and it's equal to alpha prime over alpha times the Michaelis-Menten constant. And so depending on that ratio, that Km value may increase or it may decrease depending on which one of these reactions is happening in predominance. Questions on that so far? Pretty much just everyone's just super confused. Perfect, that was my plan for today. See if I could leave everybody in utter confusion. All right. So this figure is either in your PowerPoints or it's in the textbook, which may help you just keep them sorted straight. Here are our three types: non-competitive, uncompetitive, mixed. Non-competitive is just on your worksheet here in this little square. Non-competitive is when you have one substrate binding with one inhibitor binding. The inhibitor only affects the activity, but does not affect the ability of the substrate to bind. It is so rare that it's bundled in with mixed, because it pretty much looks like a mixed inhibition. So that's why on your little sheet it's called mixed / non-competitive. They appear the same. Similar, yep. Mixed and non are pretty much the same mechanism. It's very hard to tell one from the other. So for our three types of inhibitor and then our plain non-inhibited, we have our three different Michaelis-Menten equations. Right, one, this is our regular one, Vmax times substrate over Km plus substrate. Competitive includes our alpha value. Uncompetitive has to include two alpha values because there's two different mechanisms, whatever my sheet was, that picture 2 seconds ago. And then mixed is the one we just looked at with alpha, alpha prime. And then the effect. So you need to be able, I'm not going to ask you to write out the Michaelis-Menten equation for all the inhibitor ones. Big sigh of relief. But if I gave you a graph of it, you could pull this information off the graph. If I labeled the x and y's, you should be able to at least tell me where the intercepts are. If I give you the equation, you could sketch the graph, or if I give you the graph all labeled, you could draw the equation. Megan?
Is that graph, or that chart, is it a summary of what we need to know for the test, basically, along with the
Yes,
graphs?
along with the actual pictures of the graphs, yes, yes.
The more likely we're going to need to know how to look at it.
Should be able to look at it and pull off the Line-Weaver-Burke equation, or, given the Line-Weaver-Burke equation, sketch the appropriate graph and label the appropriate points. And then, either way, you can tell me this stuff. So a competitive inhibitor increases the Km. An uncompetitive decreases. A mixed decreases Vmax, but Km could increase or decrease. So say, yeah, this one, it's the alpha, it's alpha prime? Yeah, alpha prime. From the x-intercept, for a mixed inhibitor, it's alpha prime over alpha times Km. So depending on the ratio of alpha prime to alpha, the Km value may be increasing overall, apparently, or it may be decreasing. You just need to know that that's not the one that's going to tell you the most useful information on this graph. It's going to be some of the other features.
Will be given like the alpha.
Yeah, yeah. Because maybe if I had you sketch it, I'd be like, if alpha equals 1 versus alpha equals 2, draw me that sketch, which would be this line versus that line. Right, be able to draw the no inhibitor versus any combination of inhibitor. That the slope has increased, the y-intercept has increased, and the x-intercept, depending on how you choose to draw it, scoots around at the bottom. So you should be able to summarize these points down here. These are good test questions. Competitive, uncompetitive, mixed, non. Be able to kind of fill in those blanks. Pretty much it's the stuff I wrote up here, just filling it in down here. That's a good test of your knowledge. All right, my plan now is, there's one last thing I wanted to talk about, and I'll talk about that on Friday, about allosteric regulation and how that kind of pulls together all this stuff with enzymes. But in the last 5 minutes, I want everyone to, I'll give you a sheet of paper, write down what kinds of questions you have about the chapter 6-7 material, and we'll go over that on Friday. So things you're confused about, things you want clarification on. It can't just be chapter 7. It has to be an actual question. It can be as many questions as you want. And I will get to as many as you can on Friday. Go ahead and look through your notes. Figure out what you want to be clarified on. Maybe if there's some stuff like quiz not go well. We actually registered. Yeah, I think there's so, yeah, but be able to talk about what were the assumptions you made to get with final conclusions. Right, there's 3 or 4 assumptions we have to make in order to get to the final one, and we want to do something that's otherwise what falls apart. And I don't need your name on it, it's just whatever questions you might have.